stopped working. And at some point, they bought a new camera that is completely Wi-Fi enabled that should make uploading easier. However, nobody has taught me how to use it, and I am not taking the time.
Yeah.
Like,
I think it's fine.
that's right. Exactly. Because Chris mentioned that a couple of weeks ago when I was in his office looking for something, and he was like, "So we have this like Wi-Fi enabled camera." I'm like, "Do you know how to set it up and get it working?" He's like, "No." I'm like, "Okay, well when you do, let me know and I'll come learn." But
So Sam, so it says it's streaming, but there's no preview here.
It says it's streaming.
Yeah, I'll check it.
Pull it up. My guess is that
well,
yeah. The only times we've had any trouble have been when the Ethernet Wi-Fi doesn't work. I was in the lab.
Okay, welcome back everyone. Let's get started. Hey guys. Okay, so last week we started talking about graphs, and I'll spend this lecture to continue on that, and I'll probably also need another lecture to wrap up the whole graph chapter here. So I'll likely update the scale after that. And then also on Tuesday we talked a little bit about election visualizations, and especially how like polling was visualized and how polling worked and so on. And so I guess generally we can tell this time the polling, at least the 538 model that we looked at, was pretty accurate, and the outcome basically was very much at the top of the histograms that we looked at. And after an election, it's of course interesting to look at the results. And so I found this interesting picture here on Twitter that did a visualization of the election results, of the congressional election results, and compared them from multiple news outlets. We have The Guardian, Axios, Bloomberg, New York Times, Politico, Washington Post. And what you notice here, there is actually, like, of course, there's other charts out there, but none of these charts uses coloring of the districts, like an explicit coloring of the districts. And we talked about why, or maybe why isn't that a great idea to just explicitly color code a district? We talked about this last time, but can you remember?
There's really, really small districts that have large populations.
Exactly. The size of a district does not necessarily correspond to its population, and therefore it doesn't really make a ton of sense to visualize this in actual spatial coordinates. And so here are a couple of different approaches. And so we have these like hexagons that are pinned with the Guardian, then we have these like rectangles in various formats. I guess the Washington Post has the most, let's say, interesting looking visualization here. So if you look at this, which one do you find most compelling and why? I guess the questions you should think about is, can I quickly identify a state based on what I know about the United States, about the map? And so, do you think it's easy to quickly identify a state, let's say in this map? Yeah, obviously, right? But what do we not, what's difficult to see here? The actual votes, right? They're kind of small compared to the overall map, so that's kind of an odd choice, in my opinion, because there's a lot of gray and not a lot of data in the front. Let's take a look at the Washington Post here. Can you find Utah quickly here? What about the Guardian visualization? Yeah, so the Guardian kind of is a nice compromise between abstracting the districts and also having geospatial context. So I think the New York Times takes a similar approach, but somehow, I don't know, I can't really tell why, but aesthetically the hexagons look better, in my opinion, than the New York Times, but they use very similar strategies. So I would say those two are really good encodings. Those are faithful encodings according to the principle that we talked about, but they are not necessarily, they are not so great at preserving geospatial relationships, right? So yeah, what I find interesting also about these maps is these are all major news outlets, and this stuff that you see here was really developed in visualization research community, and you can see how the influence from an academic field here happens on these news outlets, and they take some of the insights that were developed in this field really to heart. Okay, so that's a little bit of a detour. Now let's get back to graphs. We had this graph exercise last time, and then we came to the conclusion that there's two major ways of visualizing these networks. One is the canonical node link diagram, and we'll talk more about this today. And the other one is the adjacency matrix. We then talked a little bit about the applications of graphs, so that we have social networks and internet and geospatial networks and electronic networks and biological networks that all are important applications for graphs. And then we looked at this case study where we looked at the importance of social networks and various effects in our lives, and that we're not influenced only by our direct friends, but also by people at some distance. Then we talked about some graph theory fundamentals, the Königsberg bridge problem, which was the first formulation of graph problems by Leonhard Euler in 1736. And then a couple of basic graph terms. I'll skip over most of this here. We talked about hypergraphs, where an edge connects multiple vertices at once. So this is unordered, and it's different from having separate edges between nodes. Then we talked about articulation points and unconnected graphs. An articulation point, just to recall, is a vertex. So if I delete this vertex, it will partition a network. And then we talked about bipartite graphs. Bipartite graphs are those kinds of graphs that have two different node types and edges only between the two different types of nodes, but not within a single type of nodes. And then we talked about trees. Trees at its basics are graphs that have no cycles, but we also commonly treat trees as rooted trees, but that's not strictly speaking necessary. Trees can be, graphs usually are not ordered, but trees can be ordered. And then there's this reference to like all of these different named classes of graphs. Next, we talked about a couple of important graph measures, things like the degree of a node, which is a local measure of importance of a node. So that tells us how connected a specific node is to its neighbors. We looked at the degree distribution of a couple of real-life networks. Here we have a protein interaction network, which is a so-called scale-free network. And you can see that a lot of nodes have a fairly low degree, and only very few nodes have a high degree. So there's a lot of, like in a scale-free network, you have nodes that are hubs, you also have preferential attachment to those nodes, and these are very central to the network. Then we talked about a measure of global centralities, like degrees are local importance, and betweenness centrality is a measure of global importance. Betweenness centrality is measured by essentially measuring how many shortest paths go through a specific node. And if you compare the betweenness centrality to the degree distribution, we will find that there are certain nodes that are very central in the betweenness centrality measure. They are also central in the degree distribution, but degrees, there tend to be more nodes with a higher degree. Betweenness centrality is a more kind of like exclusive measure where we have the really important nodes of a network pop out. So here are the distributions of betweenness centrality versus node degree. Then we talked about path and distances, especially like a common question to ask our shortest path. That's what you basically do whenever you use Google Maps to navigate from place A to B. In the back end, there is a shortest path algorithm running and presenting you with a couple of options, Route A or Route B. These are kind of like alternatives. And the shortest path, like we'll talk about a couple of visualization techniques, how they support these path-based tasks. So this is where we stopped last time, and today I want to focus on graph and tree visualization. So this figure is really, it's true actually for all kinds of visualization, but it's especially important for graph visualization in my view, because on the one hand we have graph data, but on the other hand we have goals and tasks, right? So we have like specific questions that we want to ask. And graph visualization is rather tricky. And so we don't usually have a graph visualization technique that simply works for all kinds of questions and all kinds of data sets. And as usual, we have to find visualization techniques that work good for specific tasks given a certain data set. And so how do we decide which representation to use for which type of graph in order to achieve which kind of goal is the question that we want to ask? And in the next hour or so, we'll talk about the different options here. If we analyze the kinds of tasks that we want to achieve with graphs, I would classify them into two principal tasks: attribute-based tasks and topology-based tasks. So attribute-based tasks are those where you're mainly concerned with some properties of nodes and edges. So let's say I have a social network and I want to see like the social network of people, like my social network of people of roughly my age, right? So that means that I kind of like focus on the attribute age in this particular case. Whereas topology-based tasks are these tasks that really care about the connectivity. So questions such as like what is the shortest path between those two nodes, or what are the clusters in a network, and so on. And so more specifically, we can also break this down into localize, quantify, and sort. And there's always like an attribute-based task and topology-based task example for these. So localize is about finding a single or multiple nodes or edges that fulfill a given property. So an attribute-based task that would be, for example, find an edge with the maximum edge weight. And topology-based tasks that would be find all adjacent nodes of a given node. If you want to quantify something, like counting or estimating a property of the graph, an attribute-based task would be give the number of all nodes. A topology-based task would be give the degree of a node. If we want to sort or order, that would be enumerating the nodes or edges according to a given criterion. Attribute-based task would be sorting edges according to their weight. Topology-based task would traversing the graphs starting from a given node. So this may sound a little bit abstract. There is like a good paper that I do recommend. It's fairly straightforward. It's called Task Taxonomy for Graph Visualization It's from Bangchin Lee, Catherine Brazon, Cynthia Parr, and Jean-Marie Fouquet. Those people are really like graph visualization experts, and they really thought about the different tasks. So this is a very well-cited and fairly short paper. So if you're working with graphs ever, I would definitely recommend that you read this. So fundamentally, there are three different types of visualizing graphs. The first one is explicit graph visualization, which we also call node link. That's kind of like the thing that we always think about when we're talking about graphs. Then there's the adjacency matrix, and then there's implicit graph visualization. And as you'll see, implicit graph visualization is really only applicable to specific types of graphs, namely trees, and so they don't work for general graphs. So to start off with, let's get into explicit node link visualization. So here's our basic node link graph representation. Here we have each node is a point, and each edge is a line or an arc. And so we have these, like a very simple example here with A, B, C, D, and E. There's a couple of different layout approaches that we'll talk about. The first one is free layout. So that means that I essentially can position my nodes however I like. I don't have to care about anything else. I usually try to find a layout that is optimal for topology or for some other criterion. Then we have style layouts where we arrange the nodes according to a certain pattern. Like here we have a circular example and then a grid example. And then another common class is fixed layouts, and that really is important for spatial layout. So for example, if I want to see migration patterns in the United States on top of a map, I do want to use a fixed layout because people are moving from city A to city B. But these kinds of like fixed layouts are also common in, let's say, brain connectivity visualizations where I really want to connect certain regions of a brain, but also show, for example, the shape of the brain in the background. So those are our three major options. I think that let's start out with these free layouts. So we can actually formulate a number of criteria for a good node link layout. So for example, in a good link layout, you want to have a minimal number of edge crossing, a minimum distance between neighboring nodes. You want to have minimize the drawing area. You don't have only limited space. You want to have uniform edge length. So edges shouldn't be very different in length. You want to minimize edge bends. You want to maximize angular distances between different edges so you can tell them apart. You want an aspect ratio of your drawing area of approximately 1. And you also want symmetry so that similar graph structures also look similar so that they can identify certain patterns. And like you could debate any of those different criteria, but I would assume that you would agree that those all sound sensible. And so what usually, like in graph layouts, what people try to do is they kind of like define some kind of cost function and then try to minimize all of these or a selected number of criteria or maybe some other criteria. And so that's kind of like a common approach. However, it turns out that these criteria can be quite conflicting sometimes. So for example, minimizing the number of edge crossing versus uniform edge length. We have the same graph here represented in two very different ways. So on top here, we have like this edge from the light gray to the light gray node. We simply can avoid an edge crossing by drawing the edge up here. But of course, this edge is much longer than all of the other edges. Whereas down here, we have roughly uniform edge length. Not exactly, but clearly less problematic than at the top. But we have an edge crossing. So there's a conflict here. And then we have the question of symmetry. So showing like a parent node and 3 child nodes with exactly the same pattern, in this case, versus space utilization. So that I can, for example, show labels or so more efficiently. And so these are trade-offs that you have to make. The traditional, or let's say the most common way of creating these graph layouts are called force-directed layouts. And that's basically a physics model where we treat edges as springs that attract the nodes that they're connecting. And then we treat all of the nodes or the vertices as magnets that repulse each other. And so then we set up this physical system and run the simulation and then kind of try to come to an equilibrium. And so how does this algorithm work? So you initialize a layout by placing nodes in random locations. You can place them anywhere, but usually some really random locations are useful. And then you run a loop. while not in equilibrium, calculate the force on each vertex. And the force on each vertex or node is the sum of the pairwise repulsion of all nodes. So you look at one node and see how much is it repulsed by all of the other nodes, given the distance to the node and, of course, the force of the repulsion. And then the attraction between connected nodes. So you have the spring force that connects the two nodes, and then you sum those two up. Of course, one of them is going to be negative, the other one is going to be positive. And then you have, after you've calculated this force, you move the vertex by the direction of the force multiplied usually by a constant. And that's one iteration of this algorithm. And then you keep doing that over and over again until you reach some kind of equilibrium. So for example, a measure of equilibrium would be like the total distance that you have moved your vertices. If that is below a certain threshold, you have found the terminating conclusion and you have reached a good layout. Okay, so how does this look in practice? So here is a little video of how we initialize a node. You see that it seeds with random locations, and then it very quickly stabilizes. So that's like a network with maybe 100 nodes, and so we see that this is like fairly efficiently calculated, and we can actually see that this network is quite, let's say, quite well structured. So we can actually see these cliques or almost cliques. We can see these different clusters. We can see the central nodes. You probably recognize this network by now. This is the Les Miserables network, and Valjean here at the center. So, any question?
What is the force on the algorithm? The force, how is it represented?
The force? So we have two different types of forces. In the simplest case, we have repulsion between every node, like pairwise repulsion between each node, and you can define this however strong you want it to be, right? So that's a choice that you make as an algorithm designer. I'll show you later how we can play with this. But usually, let's say, the repulsion force is rather weak compared to the attraction force that we have in the springs, because we have, like, repulsion acts on all of the nodes, whereas attraction acts only on those nodes that are connected by the springs. So the spring force tends to be a little bit stronger in practice. But the exact values, they really change the layout, how it looks in practice. So you'll look at an example how we can flexibly define these forces. So question, what would happen with this algorithm if I don't have any edges?
It's my corner.
Yes. So the layout simply blows up. And so there's actually a stopping criterion in here, but in practice, this would be infinitely. This would expand infinitely. So let's take a look at an example here. This is a nice tool that is like an interactive demonstration of these different forces. And so what I should say, in practice, you have a couple, like these two forces are the most important part, like the repulsion and attraction based on springs. But in practice, you also have a force where you avoid collisions, so that you don't have overlapping nodes, because that's very often really important. And then you usually also have like an additional artificial gravity in the center of your drawing canvas, because otherwise your graph would float off. Yeah, so these are the most, like, you can define, like here, for example, this is the center force, and I can modify that center force, which simply moves the graph around, right? I can modify the center force in y direction, that moves the graph around. So here, this is the charge now. This is the attract or repulse nodes to or from each other. So if I decrease the charge, I get into like these kind of like, increase the charge, I get into these unstable states here. If I, like for example, switch off collision detection, I will get these collapsing networks much more quickly. Notice that this is like a much smaller hole than before. So collision detection is quite useful in common. Then we have a gravity force that can pull us into a certain direction. That's also optional, but this one here is kind of important. So now I switched off the length, the springs basically, and then now I can modify the strength of the length here. So these are all the different parameters that I can in practice iterate over here. And as you see, it can, like, this is quite a different layout than what you've seen before. I would probably say that this one here isn't quite as good as the original initialization here. So in general, we can say that these force-directed layouts provide fairly good results. They're especially good at creating graphs of uniform edge length. They're not, usually do not consider edge crossing as an optimization criteria. They make clusters commonly visible, so if you think back to the Les Miserables example, we could clearly see those cliques of characters that interact with each other. They are not deterministic because they usually have a random seed, and so therefore the layout is going to be not exactly the same every time, of course. And they also tend to be computationally expensive. So we have O of n to the power 3. And that's because we have to check the force between all node pairs in every step. And in practice, it takes about n cycles to reach equilibrium. So that's a fairly expensive algorithm computationally, which means that on a desktop computer, if you want to render something like this interactively, we can do that for approximately 1,000 nodes. In practice, we need things like damping or center of gravity to make this work smoothly. So now you could say that, well, 1,000 nodes for interactivity isn't all that great, but it actually is not that big of a problem, because if you have a lot of nodes, you end up with this like known giant hairball problem in graph visualization. So here, like I call these like giant hairball or shock and awe figure. All of those figures do is show other people, oh, I have a lot of data, right? But other than that, there's not really too much structure visible here, right? So you can see a couple of nodes that are highlighted and how they're connected. That's the human proteome, so all of the proteins interacting in a human body. Yeah, that's not much better than looking at this picture. However, if you want to address scalability, and there are sometimes reasons to do these kinds of layouts, there are certain ways of doing that. For example, you could limit the calculation of pairwise distances only to certain nodes. And one way of doing that is by first running a clustering algorithm on your graph. In a clustering algorithm, if you have pre-processed your graph with a clustering algorithm, then you could run your force simulation only within that cluster, and then run a force simulation between the clusters. And then you get like a layout where you don't have to do all of these pairwise comparisons, but have scaled down that problem significantly. So that's one approach to speed these layout algorithms up. Another layout, and I really like this paper here, is our orthogonal layouts. And orthogonal layouts, they are fairly common in these rather sparse graphs, as you have them very commonly in biological applications, like metabolic networks, for example, and signaling pathways or signaling networks look a lot like this. So they're not very dense. And then we use these like orthogonal layouts because they're kind of like easily traceable by humans. And this paper isn't really about orthogonal layout in principle, but by developing a new orthogonal layout. And so what's very common, if you look at these professionally curated pathway diagrams, they look roughly like this. And this is created by a human. So a human sits down and spends like a lot of time on creating those layouts. And this time is justifiable because each of these, like basically understanding the relationship of this node to this node, that's a PhD thesis. And so people put a lot of effort into creating those nodes. And of course people have tried also to create these orthogonal layouts automatically. And so that's kind of like the state of the art of orthogonal layouting before 2015. And so like, a group of researchers has defined these are the certain criteria, like clearly the nodes need to be orthogonal, and that's the results. And who would think that this is a better layout than this? One person. Who thinks this is a better layout? Okay, majority. So you prefer the human solution to the algorithmic solution. And so what they did is they actually did like why I really like this paper is because they did a study on how do humans actually lay out the graph. So they gave people a fairly not smart or like some kind of like non-orthogonal initial layouts for different graphs, and then they asked humans to create layouts on Amazon Mechanical Turk. So they actually let them modify those graphs. And then in the next second path, they also let humans, other humans in that case, rate the quality of the layouts. And so here we have the worst human layout, and basically you can see this Mechanical Turk here didn't do all that much. Here we have the best human layout. So you can see that this is actually quite a good representation of this network, right? So here we have the original graph, the worst layout, then we have like some medium, or here's the 16th worth layout, and then we have two good examples of layouts. And so they did that for many different graphs, for many different experiments, running two different paths of experiments. And then they identified these are the criteria that people use to create those layouts. And then they kind of like really reverse engineered the human thought process that went in and produced these layouts here that their algorithm created automatically. And here's the competition that's the best previous algorithm. And so I think that especially these here, I think are much better with this new algorithm. So the downside of this whole algorithm is two things. A, they haven't published the code. And B, it's very slow. But I hope that we will eventually get around to publishing the code, and then we can use these algorithms in practice. This is actually one best paper at InfoVis 2015. So one thing, like my research area is graph visualization, and so I have fairly regularly every semester or so somebody from a startup company coming to my office and asks me about graph visualization, and they usually bring a pair of, let's say, Oculus glasses that want me to demo their 3D graph visualization in VR or AR. I saw this picture on Twitter, and I kind of wanted to discuss with you guys, do you think a group of biologists would want to come together and discuss a network like this? Probably not. So why not? Exactly. So we have different perspectives. So that's actually one of the biggest problems of 3D layouts, right? That if we lay out in 2D, we can optimize for the one perspective we have. We can make sure there's no collisions. We can all of these layout criteria that we define, we can use them and kind of selectively optimize for them. But if we do that in 3D, as soon as we change the viewport, we kind of like have collisions and we can't really avoid them, right? So we have like this randomness factor in how we create our layouts. And then we have all of the other problems that we usually have with 3D, like the occlusion is the one that we just mentioned, but we have the thing if I want to color code them, we need to use shading. We have complicated modalities of rotation, of navigation, and so on. And so I have not yet seen a convincing example of a 3D graph layout. The only exceptions are when I have a 3D spatial data set, like for example brain connectivity. Then if I really care about the spatial context, then of course you want to have a 3D graph too. But for abstract graphs, I have not yet seen a compelling example. Okay, so styled layout. Here's an example of a styled layout with a circular ordering of the nodes. And like, what do you think is the benefit of these layouts?
Every node is visible.
Every node is visible.
You put nodes with lots of connections next to each other, so it doesn't lose.
Yeah, so I can optimize the ordering and to kind of like have neighboring nodes to be close to each other. Like basically you're already hinting at the problem that we have, that we get a lot of like edges that kind of like gets very dense. Reminds you probably of parallel coordinates. How computationally expensive do you think this layout is? Like what would you need to do? Is there any complicated algorithm?
You just need to put, I mean, if you're not optimizing, you just need to like draw, a point around the circle and then just line. So it's
Exactly. So we have basically we get this in minimal time. It's a linear layout algorithm. But the problem that we have is that it's really tough to see structure, right? So we have here about 3% of all possible edges, here about 6% of all possible edges, and it kind of is already very cluttered. So, and you can't see clicks, you can't see like which is the most connected node in here. Really hard to tell, right? In a force directed layout, you would quickly see that. If you have special cases, this can be actually a good choice. So here is a case, this is a calling graph of, I think it's Flex, which is a Flash-based visualization library that nobody uses anymore. But essentially we have the package structure here. Like these are the high-level folders. Then we have software packages, and then we have individual functions in the circle here. And then the lines here are calling graph, are basically the calling graph of that, right? And so here that kind of like, because we have a sensible ordering, as you mentioned earlier, that does make a little bit more sense. But still, it's very cluttered. But then people realize that we can actually use this hierarchical structure here to optimize the routing of the links here. And we can use a bundling strategy to create this kind of layout. And so that is actually not a bad layout, right? Because here I can fairly quickly see this module here seems to be very central to the whole program. It's been called by a lot of, I don't remember the directionality, but it's either calling or called by a lot of different functions. And so how does this work? So the idea here is that essentially what happens is behind the scenes, we have like let's say we have a node here, we have a node here, we have a node here, and then we have a connection like this. Okay, what they do is they kind of invert that. Okay, and then they route each link through those points here. So basically, this is what you see in this figure here. We have the structure that goes outwards, flipped over to look inwards, and then we have these bundling points, and then the lines, like if we look at this example here, then this is like the source destination, and now instead of having a direct connection, we route this link across the shortest path here. And the shortest path are trivial to find because these are trees. And then we use a spline instead of a line, and that's how we get this nice routing. And this depends now, of course, the spline. We can customize the spline according to a bundling strength, which they call beta here. And this beta influences how tight these nodes are bundled. So here we have a beta of 0, and then here we have a beta of 1, and in between 0.25, 0.5, 0.75. So which do you think looks the best and why? Yeah, I hear people saying 75, because we have like a nice compromise between bundling strength, right? But it doesn't completely occlude where things are coming from, like the 1 here. So this paper is like also a best paper from 2006. But that kind of like introduced this whole idea of bundling. So now the downside here is that I have to have a hierarchical structure backing that. Here is an example, like this is implemented in D3. You might have seen this. And here I can like basically, they call it tension here, what we called beta earlier. I can manipulate the tension here dynamically. So this works only for if you have a tree. But then people like really liked this paper and thought a lot about how can we generalize this to other layouts where we don't have this hierarchical structure. And it turns out that you can use force-directed layouts, but now instead of just pushing and pulling the nodes, you separate each link into many, many segments. And then you have attraction between these link segments. And then you have so here would be an unbundled network, and this would be a bundled equivalent of that network that simply works by doing these attraction force simulations between these link segments. So looks quite good, right? What do you think is the downside of this algorithm? Yes, especially in those fixed layouts, you suddenly get you take paths that might not be meaningful in the first place, right? In geospatial context, you have to be worried about that. And also, as you can imagine, now that I've split every link into many segments and I have to do a force simulation between those many segments, this is very computationally expensive. So that's not usually a good interactive visualization. You rather do this as a static chart. One approach to deal with these large-scale networks is aggregation. And so the principal idea of aggregation in networks is that we define supernodes. And supernodes are essentially just aggregates of nodes. So here we have an example of a network. The black dots are the original network, and then we create these supernodes through whichever means. And then we have created this abstract representation of that network. And depending on how well I chose the supernodes, this could be just as informative, and of course, depending also on the task, than our original network. And you can commonly define those supernodes manually, or you could use some categorical attributes of the nodes, or you could run some clustering algorithm and simply group the nodes by using this clustering algorithm. And for example, if you use a hierarchical clustering algorithm, you could very dynamically define how many supernodes you want to create in a network. Here's an example where this is done in a data-driven way or in a manual way. This is a paper that I really like by Jörg van Wijk and Stefan and Elson. Here we have a fixed layout, and they essentially define certain geographic locations in that case, and then aggregate these geographic locations into this abstract graph. This is a data set of migration patterns, and so we can see that we have Seattle to Los Angeles to New York to Florida migration highlighted here, well, I'll show the video.
Roughly 3,200 nodes and 80,000 edges. There are 40 node attributes and 10 edge attributes. We can change the projection of the network to all available multivariate attributes. Here we change from a force-directed layout to H versus income. We can also change to a geospatial representation of the network by projecting the node attributes latitude and longitude. We start the exploration by creating a selection of interest. Selections can be refined by direct manipulation using the drag handles. The affected ranges in the attribute view are updated. Selections can also be controlled with the scented widgets. We can also set ranges for non-projected attributes. Now we add another selection. Initially, edges within a selection and between selections are shown. These edge attributes can be changed similar to the node attributes and are treated as a nominal edge attribute. Here we show some examples of enabling and disabling different edge types, such as between and background edges. Now we also filter the second selection on a non-projected attribute and rename both selections. The selection label.
Okay, so the main point here is that you have a complex spatial layout, and then you have some kind of user-driven, data-driven criteria of inclusion, exclusion, and then you have a very abstract representation of this data. And from this data, we can actually read that, for example, there is a lot of migration within this blue segment here, in the northeast, and there is fewer migration within this red segment, probably because it's less populated, right? And then we see that compared to the migration within the network, the blue part, that's kind of significant, but between those two parts is much less so. And that's like this kind of like data is much more difficult to see in the original chart. So here the supernodes really kind of like get the gist of the question, and by flexibly defining the supernode, I can answer a lot of different questions. We can use node link diagrams, of course, also for trees. For trees, we have very good layouts that are very old, the Rheingold-Tilford layout, for example, and they work quite well. Here we have two examples of the same layout, one applied radially and one applied in a linear layout. Of course, the benefit of the radial layout is that I can fit a larger tree on the screen, and the benefit of the linear layout is that I have labels that are horizontal and I can easily read them. So pros and cons, but these are fairly simple to do, and we have a really good understanding. On this link here, there is a detailed discussion of all of these different tree layout algorithms. You probably remember from the very first lecture, the mother of all demos by Douglas Engelbart that I showed. They actually, in this mother of all demo, they also showed tree aggregation. They had like this drill down, roll up in trees, and unbalanced drill down and roll up as well. So basically, this is from '68, and not too much has changed in the tree layout since then. In terms of interaction, we of course want to be able to dynamically grow trees. So you all know this from, let's say, a file explorer on your hard drive. Can now observe what was that? It's not great. Okay. So here we can dynamically expand the tree, and the Rheingold-Tilford layout is adjusted as we grow the tree, and the dark nodes are the ones that we can expand. An extreme example of trees are phylogenies, the tree of life. We have these phylogenies are really massive trees. We have millions of species, and phylogenies, as you can imagine, we don't have ground truth on them. So we don't actually know exactly how the tree of life works. Historically, people used taxonomy, like looking at features of, let's say, any kind of creature to kind of classify them and infer their connections. Nowadays, this is mostly done by gene sequencing, but still, this is ambiguous, and we really want to compare tree configurations like that. And this is what this paper is about. This is also notable for being the only InfoVis paper ever published with SIGGRAPH.
Biologists are often faced with the task of comparing many similar phylogenies, that is, trees that describe evolutionary relationships between species or genes. Although some sophisticated tools for tree manipulation exist, for instance when played as shown here, they are designed for small data sets of dozens or hundreds of nodes, and they have very limited support for comparison between trees. The spread of DNA sequencing is leading biologists toward the creation of much larger trees, thousands of species today, and millions within the coming few years. We present Tree Juxtaposer, a new tree visualization tool supporting scalable comparison and navigation of phylogenetic trees of over 300,000 nodes. Even small trees are hard to compare with visual attention alone. Linked highlighting of nodes and subtrees helps. Perfect matches for named leaves are easy to find, but computing the best corresponding nodes in the interior required a new algorithm that runs in n-log n time at startup. Highlighting alone can still lead to false negative conclusions. We see two leaves highlighted in exactly the same spot on both sides, but their structural relationship to the rest of the tree differs. We can mark the exact place in the tree where structural differences occur, using the results of the corresponding node computation. Subtrees underneath the black edges are guaranteed to be contiguous on both sides. The red edges show where a subtree from one side maps to a non-contiguous area in the other. Mouse over highlighting also allows us to check this property on the fly. Biologists call continuous subtrees a clade, and determining whether a clade in one tree is also a clade in the other
Okay, so I don't want to spend too much time on this, but this kind of like hints at the big problem and a very active research area in visualization, that's tree comparison or evolving trees. I'm not going to go too much into detail about this, but it's a really difficult task because graph visualization, like even tree visualization, is still like complicated relatively, and then comparison and evolving trees or graphs are especially challenging. Okay, so if we reflect a little bit on these explicit representations, the pros are that we are able to depict all different types of graphs. They can be easily customized by weighing different layout constraints. They're very well suited for topology-based tasks. But however, on the downside, they're usually like a computational optimal graph layout is NP. Even just achieving minimal edge crossing is already an NP. Heuristics are still slow and complex. For example, the naive spring embedder is O of n to the power 3. And generally, we have in these explicit representations a tendency to clutter, so they're not extremely scalable, especially when our network becomes dense. So the other main, actually, before I go into the other main visualization technique, I have a design critique prepared for today. And of course, this is going to be about graphs, and you'll need your computer. This is the Connected China project. This is a project that was developed by Fathom, which is a Boston-based visualization startup for Reuters, and it shows you political power in China. So take 5 minutes to study this, discuss it with your group, and then we'll discuss it here.
Yeah. So.
Okay, so let's talk a little bit about this. What kind of data are we seeing here? Let's start with this one here. So what's the data that we have here? What are the nodes? People, yes. But then we have also these other types of nodes here. These categories, yeah. So we essentially, they have classified those people into certain categories. How do you think does this work behind the scenes, the layout? Like, did you see what happened when I moved this stuff around? What is it indicative of? Force. Yeah, so it's a force-directed layout. And so what is the data? Like, we have nodes. Is it a graph? So why are there no edges? Raise your hand, please.
There would be too many to show all of them, so they allow you to interact with the nodes to show you edges that are relevant.
Exactly. This is not a very big graph, but they chose to only reveal edges on selection, right? So when I hover over any of those people, they are actually connected to like their whatever relations in that case. And if they were to show all of the connections, they probably wouldn't be able to do like this layout based on the categories here. So they're trying to show both attributes of the nodes by encoding it in the layout and the relationships between them. Okay, so now if I click on a specific node, let's do Xi Jinping. If I mispronounced it, I'm sorry. What happened now? So how is this network now displayed? I hear a tree, and so specifically this is a spanning tree up to a distance of 2 from this person, right? So we have the center of the node here, and then his direct first-degree connection, and then his indirect second-degree connections. And then when I hover over any of those people, we can see who he is liked by, or purportedly close to, well, related to is actually on the same level here. So here is father and mother and so on are listed on the same level. So what does this like? What's the role of interactivity here again? Why don't we see all of the links all the time? Yeah. So they really care about the specifics in this visualization, right? They care about who are the people and how are they connected to somebody else, and therefore they have a lot of labels, a lot of data to show, and that would just be quite dense in the first place. And actually, we do have like an important piece of topological information, anyways, because we have the first degree and second degree. We know at least with respect to the root exactly how they are connected, and we can switch according to different like ordering criteria here. And then we have different diagrams here. I'm gonna, in the interest of time, I'm gonna skip over the institutional power, but look at this one here. So what is the data that we see here? Exactly, the career advancement. So what can we tell from that? What does it take for me to become president of China? Can I just like be nobody and suddenly be in power? No, there is like a succession, right? You have to go through the ranks. And what's the other data that's encoded here? Years, exactly. So we have either years or, I think more interestingly, actually, age. And then, not surprisingly, we have a couple of, there's like this main trend of people progressing through the ranks and then retiring. But then the people at the very top, if we hover over the Politburo Standing Committee, we can see that people like Xi Jinping, he actually was promoted fairly fast through the different levels of the hierarchy. So, for example, like deputy for a short time, and then actually has not been on the like a deputy on the national level, but was directly a chief on the national level and became then one of the top leaders in fairly short time. And I can switch between the year and the age here. So, generally, what do you think about this visualization? Do you find it effective? Only after I explained it. So it wasn't discoverable for you? So what did they do about discoverability though? Like I skipped over that, but they have these guides, right? So you click on something here, and then if you read all of that, and you can see, of course, kind of like you have this stepper-based storytelling as we talked about previously. And then you can go into this like martini glass structure, as we called it previously, where you then now can freely explore. So that's kind of like a very sophisticated way of exploring these relationships. So yes, but I hear it's complicated. Generally, anybody else find this? Yeah?
It was really useful for looking up specific pieces of information rather than seeing huge trends.
Yes. So this is a really good observation. It's very much focused on understanding the details of relationships and understanding like the power network of one person, and maybe something new happened in the news and you want to understand what are the relationships between those people, why is this person promoted, kind of find something in their social structure that kind of like explains the rise of a person or the fall of a person.
Could we say that this is a mix between author-driven and reader-driven?
Yeah, exactly. So we start out with the author-driven, with the storytelling aspects where we have the stepper, and then we're released into the open and can explore ourselves. So that's exactly a mix between author and reader-driven.
And that's called
Martini glass, yes. In this case, it's actually a whole cabinet of martini glasses because we have all of these different ways into the story through these different aspects of power in China. So who do you think is the audience of this visualization? Like, who feels they know a lot of those people here?
Maybe expat Chinese Americans or Chinese.
Yeah. So, do you think this would, like, the New York Times would run something like this? Yeah, it maybe is a little bit too specific, right? And this was run by Reuters, and that might be like, who could be interested in exploring that? Political scientists, or maybe somebody who wants to really get a good understanding of political power in China and kind of like maybe do business in China at some government level and kind of dig into that. So this is kind of like, it's by a news agency, but not by a mainstream news agency that you would go to every day, right? And it's kind of like not an expert system, but also not like a consumer system. So do you guys like this? Generally? Any comments? Opinions? Yeah?
I don't particularly like the force-directed part, especially when the nodes are like sliding past each other. I don't think it benefits the visualization at all.
Yeah, that's true. Like the and also like the force-directed part here. I guess it's a way of implementing it, right? But you could make it static. You could recalculate the certain layouts. Other comments?
The of the bipartite.
Yeah, if I click on a node here, is that what you mean? Yes. Yeah, I think that is actually quite a good idea, and we'll see some other approaches that do that. Like a spanning tree, extracting a spanning tree from a network really lets you explore the neighborhood of a particular node very well, and that's a very flexible way of doing that. So I think this is actually my favorite piece about this visualization. Is this layout here. Implementation detail here. What do you think was this written in? Does it look like D3? It could be, but it's completely without a library. Everything here is handwritten in Canvas.
Really?
Yeah. So I know the people who did that, and I talked to them about that, and they basically make their own stuff because they say we want super custom things. They don't use libraries like D3. Okay, great. So now, any other comments? If not, let's move on. The next thing I wanted to talk about is the matrix representations. That we already talked about when you design it. And so the matrix representation is, instead of having a node link diagram, I use an adjacency matrix. Here are like a simple node link diagram and the equivalent adjacency matrix. Just to recap, how do we read this? If there is a filled-in cell between a row and a column, that means there's an edge. So for example, here we have A to A, there is no self-edge. So therefore, this cell isn't filled in. There is an edge from A to B. as you can see here, A to B. There is an edge from A to C, as you can see here, but no edge from A to D or A to E, as you can see here. So those are missing. Okay, so now, what do you notice about this adjacency matrix here? It's symmetric, exactly, because we have, we don't have directionality in the edges. If we had directionality in the edges, we could say, like, the from A to B is one direction, and we use, like, essentially one half of the symmetrical part for in edges and the other half for out edges. Here are a couple of examples of how common structures look like in a matrix representation. So a star looks like this. Note that these are directed examples here. This completely connected but directed graph looks like this. Then basically a more or less bipartite relationship. We have this block here, and then a fairly complex relationship looks like this. So do you find those very intuitive to read? Can you quickly grasp the structure of the topology? No. Not so much, right? But as you can see, there are a couple of things that are fairly easy to do with them. So first, they're really well suited to do neighborhood-related topology-based tasks. So for example, if I want to understand what are the neighbors of B, an adjacency matrix is great for that, because I just have to look at the B row and I immediately see, oh, B is connected to A, C, and D. So that's really easy to do. But if I want to say, in this example here, how is A connected to B, that's quite tricky, right? So topology-based tasks at a certain distance are really difficult to do. So I actually, I have to sit down with a pencil and trace a path. So it's really not intuitive. You have to take multiple hops. So they're not suited for path-related topology-based tasks. Again, here's a visualization of a couple of structures where we have some clicks, biclicks, or clusters. As usual, when we talk about matrix layouts, the order is critical. So here is this example. We have basically, or we start out by this adjacency matrix, like this one now, is sorted by alphabetically, which is like pseudo-random. And you don't really see too much of the structure here, right? But if I actually cluster it by frequency, then we start to see some patterns. So the most connected nodes are at the top. But if I actually do this in a smarter way, using some automatic clustering algorithm, I can clearly identify those clicks. And so we can spot these like densely connected clicks, and then we can spot the central nodes by looking at the stars. So here, Jean Valjean in our Les Miserables network, he has a lot of connections. This is a star that kind of like is quite obvious. And then we have other people here, like Gavroche, who's another main character, who is quite well connected in like here in this directions. So there's a lot of research on finding optimal ordering in these, or good orderings in these kinds of matrices. There's like a paper around matrix seriation algorithms, and there's actually a good library. So if you want to use these adjacency matrices, there is a good JavaScript library for creating those seriations. So the pros of these matrices are they can represent all graph classes except for hypergraphs. We haven't talked too much about hypergraphs, but it's not possible to show hyperedges in a matrix. The focus is on the edge set. It's not so much on the node set. So as you can imagine, if I have a completely connected graph, then I might actually be actually quite well off with a matrix representation, right? So for example, let's suppose I have like a flight data set, and airports are like tend to be quite well connected, especially if you consider like also, or if you allow like hops in between. If you say, okay, connections between airports at a distance of 2, you probably have a very highly connected network, right? And then showing this in the node link diagram is probably not the best choice. Probably you want to use a matrix representation for that. It's of course very simple to create the layout. It's just a simple grid. We don't have to do any force-directed simulation or anything like that. It's well suited for attribute-based tasks to edges. So in the flight example, I could like count how many edges are connecting these airports, and I could color code the strength of the connection very easily. That's much trickier to do in a node link diagram. We'll talk more about this later. And as we said, neighborhood-related topology-based tasks is good. Cons is quadratic screen space required. So if you had like in the Levis-Raven network had maybe 100 actors and completely filled out the screen, and they don't really work for path-related topology-based tasks. So this here is a special case, genealogical data. Genealogies are networks. They are like, well, the example here is The Simpsons. You see we have Marge and Homer. And then the children, Bart, Maggie, and Lisa. The sisters of Marge, Patty and Selma, and then the parents of Marge and Homer. I'm going to just show you the video.
Represent genealogies, a novel interactive visualization technique for large genealogy datasets based on a layered matrix representation. This representation has no crossings, which makes it more scalable than the traditional genealogy visualizations. For example, here is a genealogy of 700 individuals presented by genealogies, and the same genealogy represented by a node link diagram. Let's start with a simple genealogy of the Simpsons TV series. The basic elements of the genealogy visualization are generations, individuals, male and female, families, and relationships within families. By family, we refer to nuclear families consisting of two parents and their children. For example, in this family, the square above the family indicates that Homer is the father, and the circle that Marge is the mother. The circles below show that they have two daughters, Mikey and Lisa, and one son, Bart. Similarly, Marge's parents are Jacqueline and Clancy, and her sisters are Selma and Patty. More generally, cells above the family icon point to the parents of the family, and cells below to the children. Cells on the left of individuals show which family they were born into, and cells to the right show in which families they participate as parents. In the Greek pantheon, for example, Zeus is a father in more than one family. He married Hera, with whom he had 4 children, and coupled with other individuals, including one from a different generation. We implemented the genealogical visualization in an interactive genealogy exploration system. The system...
Okay, so what do you think about this? Any thoughts?
It's a challenge to follow. You get used to it, but it takes some time to really understand the different columns and all the links.
Yeah, so it's clearly a technique where you need to learn a little bit. And I think it's also important to have the interactivity. Because like if you click on a node, the family is, like even though you could strictly speaking read it from a static image, but it's just much easier to follow if you have the highlights. Yeah?
It's very hard to read, isn't it? Because like we have, for example, father and mother, or something, we are differentiate.
Yeah.
So we have to keep track of the shapes as well as the flow.
Yes. So I would say this is like a visualization that is maybe better catered for an expert audience, right? For historians who study these very large genealogies, I would not recommend this to be included in Ancestry.com for your usual customers or something like that. It turns out you can actually create hybrids between matrices and node link layouts. Because like matrices have the benefit of being really well suited for very dense layouts. But then they also, like if you have dense clicks that are connected, you kind of like increase your screen space by adding all the nodes to the matrix. And kind of this is what this technique tries to overcome. This is node tricks. And here, the dense clicks are shown as adjacency matrices, and then they are connected with links to other parts of the network where there are fewer connections, for example, or even to individual nodes and links. I'm not going to show the video here in the interest of time, but you can basically define which part of a network to visualize in a matrix or in a node link diagram. One problem, of course, with matrix representation is that they use a lot of screen real estate. And so we had this idea of using supernodes and aggregation for adjacency matrices for node link diagrams, and you can use the same idea for adjacency matrices. So here we have a node, and then we have defined the hierarchical structure on top of this node of this graph, and we can see that we have kind of like in these, like as we had in the previous example, A, B, C are well connected. Then here this cluster is fairly well connected, but there's no connections here and here. And so we could actually kind of roll this up into a higher order representation by defining those three here as clusters, and then representing it like this, right? So we have between J and I, we have 5 connections. Between K and J, we have 3 connections, and so on. And this kind of like extends the idea of supernodes to adjacency matrices. And of course now we need to count how many edges are filled in that case. And here it's represented as numbers and additional shadings. We can also do higher order connectivity. So this is the example that I showed earlier with the flight data set, where we have not only immediate neighbors, but we can basically define a distance function that includes multiple hops. And so here we have connections from Minneapolis to airports in Washington, Oregon. And we see that, for example, Minneapolis is quite well connected to Portland PDX by looking at the darkest dot here. We can see that, for example, there's no connection from Grand Forks to any of those airports up there. In the interest of time, I'll show the video here next time, and I'll continue talking about graphs on Tuesday, and then we'll keep talking about, I think aggregation is next on Thursday.